In this equation, we have a physicist experimenting with the effects of magnetic fields on moving charges. We have an apparatus that let particles move freely, and inside we have some varying electric fields and no external magnetic fields. In one trial run, we have protons, that's these charges here. They move straight in the x direction with a speed of 0.1 c, where c is 3 times 10 to the 8 meters per second. The protons move parallel to each other in this run with a separation of 10 nanometers. Find the magnetic force of each proton on the other proton. Okay, so there's kind of a lot to unpack here, even though it's not a terribly difficult problem. So let's label our charges 1 and 2. So my upper proton will be 1, my lower proton will be 2. Find the magnetic force. Let's start with finding the magnetic force on upper proton, the top proton. So the magnetic force on 1. Why does this experience a magnetic force? Well, it's a moving charge, so we know that only moving charge experiences magnetic forces. It must be sitting in a magnetic field. What makes that magnetic field? Well, charge 2 is a moving charge, and we know from the Biot-Savart law, moving charges make magnetic fields. So 2 makes a field, 1 moves in it, so 1 feels a force. So force on 1 is due to its motion in field created by 2. Let's write down how we find magnetic force. So F on 1 is equal to charge 1, because the force is on charge 1, times velocity 1, crossed with the magnetic field made by charge 2. So charge 1 is a proton, it's plus e. My velocity 1 I can write as v in the I direction, or 0.1 times c in the I direction. Let's put in our coordinate system. What else? The magnetic field created by charge 2 would be given by the Biot-Savart law that says mu naught over 4 pi times q2. Here we'll remember that q2 is also a proton, times v2, crossed with v2 is exactly the same as v1, crossed with r hat. Let's pause and remember what r and r hat are. R is from charge 2 to charge 1. I don't want to draw too much on top of here, but I've got charge 2 down here. I've got charge 1 up here. R is from here to here. That's my 10 nanometers. R hat points from 2 to 1. That's R hat. So R hat is equal to J hat. Okay, so let's figure out the direction of the magnetic field here with our right-hand rule, and let's figure out the direction of the magnetic force, just so we have an idea of what's happening. So the direction of the magnetic field at charge 2 is going to be given by the direction of v2 cross r hat. So v2 points this way, r hat points this way. The direction of the magnetic field at 1 is going to be out of the page. So there's the magnetic field created by charge 2. What about the direction on force 1? Well, we know force is qv cross b, so v cross b gives us a force that points down. V cross b, force on 1. So we've used our right-hand rules to think about our directions, even though we're still going to calculate all this stuff. This is kind of an interesting thought. We went through in our lectures, if we have 2 current-carrying wires, if the current flows in the same direction, the force between them is attractive. We're kind of seeing the same behavior here, right? Because 2 moving charges is not that different from 2 current-carrying wires. Okay, let's keep going with finding our magnetic field, and then let's use that to find our magnetic force. So B2 is mu naught times 4 pi times Q2. V2 is the speed in the I direction, crossed with r hat, that points up, so that's j hat, divided by r squared. So now I can take this a little bit further because I know I cross J is equal to K, and this gives me that my B2 is going to be equal to mu naught times 4 pi times my charge 2, and that's the fundamental charge, times V times K hat divided by R squared. There's an expression for my field B2. I can go ahead now and use that to find my force on charge 1. So my force on 1 is Q1, that's the charge on a proton, which is E, times my velocity 1, which is Vi hat, crossed with B2, which is this expression that we just figured out. Okay, let's neaten this up a little bit. E times E, that's going to give us E squared. V times V, it's going to give us V squared. I've got my R squared in the denominator. And I've got my mu naught over 4 pi. And I've got I cross K hat. I cross K hat is equal to negative J hat. So my force then is minus mu naught over 4 pi, E squared V squared, R squared, J hat. So there's my force on 1. Let's not finish here. Let's go ahead and put some numbers in because we were asked to find the force. So that's minus 4 pi times 10 to the minus 7 Tesla meters over amps times E squared 1.6 times 10 to the minus 19 coulombs squared. V squared is 0.1 times 3 times 10 to the 8 meters per second. Don't forget to square that. Dividing by 4 pi times R squared. R was our 10 nanometers. Squared. Don't forget our direction. That tells me that the force on 1 is equal to negative 2.30 times 10 to the minus 14 newtons J hat. So there's my force on charge 1 due to its motion and the motion of charge 2. All right, next we're asked to find the magnetic force on each proton. So we don't only want the force on charge 1, we also want the force on charge 2. You've got two strategies here. You could go through the motion of charge 1 and find the field it makes at charge 2. Then charge 2 is moving in that field. You could find the force it feels going through exactly the same method. Or we could recognize that if 2 exerts a force on 1, then 1 must exert an equal and opposite force on 2. We can use Newton's third law here. So from Newton's third law, the force magnetic on 2 must be equal and opposite of the magnetic force on 1. So it's going to be plus 2.30 times 10 to the minus 14 newtons J hat. So equal and opposite, same size, opposite directions. Okay, part B, find the electric field surrounding each charge. So what we saw is that our charges experience a magnetic force. It goes straight through, so there must be other forces happening. Let's think about those forces. I can think of two other forces that must be happening. First of all, I have two positive charges close by. I know they repel each other through Coulomb's law. The second is that these plates are creating electric fields, so these charges must feel electric forces. Okay, we want to find the electric field. Let's draw a free body diagram. Let's use the fact that they go straight through to tell us that the acceleration is 0, and let's see if we can calculate the field. So we'll start with the free body diagram. And why don't we start with charge 1? So here's my proton, my charge 1. I know that the magnetic force on charge 1 points down, because we found that now in part A. I know that it's repelled by charge 2. I'm going to say that's F12 for the electric force between charges 1 and 2. Now I know it also feels an electric force because it's in an electric field. I don't really know the direction of that force. I'm just going to guess that it's down. I'll be careful with my math, and the math will tell me if I'm correct or not. And I know that charge is moving straight through to the right. So if I write Newton's second law, the net force on charge 1 is mass 1 times its acceleration. That tells me that my Coulomb repulsion between the charges plus the magnetic force plus the force due to the electric field all have to give me a vector sum of 0. Okay, my Coulomb force between my charges, why don't I go ahead and calculate that? So between 1 and 2 has a magnitude of k times the size of charge 1 times the size of charge 2 divided by the distance between them squared. K is 8.99 times 10 to the 9 newtons meters squared per coulomb squared times Q1 1.6 times 10 to the minus 19 coulombs times Q2, so that's squared, divided by R squared, which was 10 nanometers. Put that through the calculator, I get 2.30 times 10 to the minus 12 newtons. Okay, and that electric force points straight up. So for my Coulomb force of repulsion between them, I have plus 2.30 times 10 to the minus 12 newtons, J hat. My magnetic force was minus 2.30 times 10 to the minus 14 newtons, J hat. For my electric force, that's my charge, E, times my electric field, 0. Notice I've been very careful about my vector notation. That means when I solve for E, this solution will give me the direction of the electric field. So then E is going to be 2.30 times 10 to the minus 14 newtons, J hat. Subtract 2.30 times 10 to the minus 12 newtons, J hat, divided by the charge E, to give me an electric field, which is minus 1.42 times 10 to the 7 newtons per coulomb, J hat. Okay, so there's my electric field in this region. So it points down with a magnitude of 1.42 times 10 to the 7 newtons per coulomb. What about for charge 2? So we can go through this process again. We'll be able to reuse a bunch of the numbers. So on 2, let's draw the free body diagram. Here's charge 2. I know it feels a magnetic force, which points up. We talked about that in part A. It feels an electric force of repulsion because it's near another positive charge. And then for this one, I'm going to guess that the electric field points up this time. I'll write down my Newton's second law expression. The net force on charge 2 is mass 2 times its acceleration. So my net force is going to be my electric force, which is E times E, plus my magnetic force. Take away my Coulomb force. Has to be 0 because this one goes straight through as well. Solve for my electric field and I get plus 1.42 times 10 to the 7 newtons per coulomb, J hat. So that's the electric field that charge 2 is sitting in.